When considering electric versus diesel fire pumps, several factors influence the decision, primarily revolving around cost, reliability, and environmental impact. Let's delve into a comparison of both types. Electric fire pumps generally have a lower initial cost than their diesel counterparts. Electric motors are typically less expensive to purchase outright compared to diesel engines. Over time, electric fire pumps tend to have lower fuel costs. The cost of electricity is generally less than the cost of diesel fuel, leading to reduced operating expenses over the pump's lifespan. Furthermore, electric motors typically require less frequent and less intensive maintenance compared to diesel engines, contributing to lower overall maintenance costs. On the other hand, diesel fire pumps present a different set of considerations. The initial cost of a diesel fire pump is usually higher due to the more expensive diesel engine. Diesel fuel is typically more expensive than electricity, resulting in higher operating costs for diesel pumps. Diesel engines also require more frequent maintenance, including oil changes, filter replacements, and injector cleanings, which increases maintenance costs. Beyond these basic cost comparisons, there are other important factors to consider, particularly when evaluating electric fire pumps. Electrical infrastructure upgrades may be necessary to support the new fire pump. The existing electrical service might need to be upgraded to accommodate the additional load, including the installation of a new tap ahead of the main switch and possibly upgrading the service equipment itself. Communication with the local utility company is crucial. Coordinating with the utility ensures that their service can adequately handle the increased electrical load and that there is no unacceptable voltage drop when the pump is operating. Reliability is another key factor. In areas prone to frequent power outages, a diesel pump may be a more reliable backup power source, as it is independent of the electrical grid. Finally, environmental impact is an important consideration. Electric pumps generally have a lower environmental impact than diesel pumps because they do not emit exhaust gases. The decision between an electric or diesel fire pump hinges on a comprehensive evaluation of several factors. The lower initial cost of an electric pump could be offset by potentially higher operating costs depending on electricity rates. The availability of a reliable electricity supply is critical. If the facility experiences frequent power outages, a diesel pump might be the better choice, irrespective of cost. Environmental regulations in some municipalities may favor electric pumps over diesel pumps due to emissions concerns. The facility's maintenance capability should also be considered, as diesel pumps require specific maintenance procedures. There are also aesthetic considerations. Electric pumps may be preferred due to their reduced noise and the absence of exhaust emissions. In most scenarios, an electric fire pump represents the most cost-effective and environmentally friendly option. However, a thorough analysis of the specific site conditions and project requirements is necessary to reach a fully informed decision. When considering the electrical upgrades, it is important to first determine the fire pump motor's full load amps, or FLOW from its nameplate. This value represents the current the motor draws when operating at its rated horsepower and voltage under full load conditions. The National Electrical Code, or NEC, provides guidance on sizing conductors and overcurrent protection for fire pump motors. Specifically, NEC Section 430.22 addresses conductor sizing, stating that the conductors supplying a fire pump motor must have an ampacity not less than 125% of the motor's full load current. This is to account for the fact that fire pump motors are expected to operate continuously under heavy load conditions. For example, if the fire pump motor has an FLA of 100 amps, the conductors supplying it must have an ampacity of at least 125 amps. Next is to choose the correct overcurrent protection for the fire pump motor circuit. The NEC provides specific requirements for fire pump motor overcurrent protection in Section 430.31. Unlike standard motor circuits, fire pump motor overcurrent devices are intended to protect the conductors and components of the circuit, not necessarily the motor itself. This is because fire pumps are considered critical life safety equipment, and it is more important to keep them running during a fire event than to protect the motor from damage due to overload. The overcurrent device must be sized to carry the locked rotor current of the motor indefinitely. The locked rotor current, or LRC, is the current the motor draws when it is first started and the rotor is not yet turning. This value is typically much higher than the motor's full load current. The NEC allows the use of inverse timed circuit breakers or fuses for fire pump motor overcurrent protection. The trip setting of the circuit breaker or the rating of the fuse must be sized no greater than 300% of the motor's full load current. This large overcurrent protection size is necessary to allow the motor to start without tripping the overcurrent device due to the high inrush current. Fire pump controller plays a crucial role in the operation and protection of the fire pump motor. The controller provides automatic starting and stopping of the motor, as well as monitoring and protection functions. Fire pump controllers are specifically listed for fire pump service and must meet stringent requirements. The controller includes a manual start switch that allows for manual operation of the pump, as well as an automatic start input that initiates pump operation upon detection of a drop in water pressure in the fire protection system. The controller also includes various indicating lights and alarms that provide information on the status of the pump and the system. One of the most important functions of the fire pump controller is to provide motor overload protection. However, unlike standard motor overload protection, fire pump motor overload protection is intended to alarm only, not to trip the motor. This is to ensure that the pump continues to operate even under overload conditions. If the motor is subjected to a prolonged overload, the controller will activate an alarm to alert personnel of the condition, but it will not shut down the pump. The fire pump circuit must be provided with the disconnecting means to allow for electrical isolation of the pump for maintenance or repair. The disconnecting means must be readily accessible and located within sight of the fire pump controller. It must be suitable for use as service equipment and be lockable in the open position. The disconnecting means must be horsepower rated to match or exceed the horsepower rating of the fire pump motor. The power source for a fire pump must be extremely reliable. The NEC requires that fire pumps be supplied by a dedicated electrical service that is separate from the normal building service. This is to ensure that the fire pump will continue to operate even if the normal power supply is interrupted. Fire pump service must be run in a raceway that is installed separately from other building wiring. The raceway must be fire rated to provide protection from fire damage. The fire pump service must be provided with overcurrent protection at the source. The overcurrent protection must be sized to protect the conductors and equipment of the fire pump service. The overcurrent protection must be coordinated with the fire pump motor overcurrent protection to ensure selective coordination. Selective coordination means that only the overcurrent device closest to the fault will operate, minimizing the extent of the power outage. The NEC provides detailed requirements for selective coordination in Section 700.27 for emergency systems and Section 701.18 for legally required standby systems, both of which may apply to fire pump installations. Proper grounding of the fire pump system is essential for safety. Fire pump motor, controller, and all associated equipment must be properly grounded in accordance with NEC Article 250. The grounding conductor must be sized in accordance with NEC Table 250.122. The grounding conductor must be connected to a grounding electrode system that meets the requirements of NEC Section 250.50. The grounding electrode system may consist of a metal underground water pipe, a ground ring, or other approved electrodes. Regular testing and maintenance of the fire pump system are essential to ensure its reliability. The NEC requires that fire pumps be tested weekly and annually in accordance with NFP 825, the standard for the inspection, testing, and maintenance of water-based fire protection systems. Weekly testing involves running the pump briefly to ensure that it starts and operates properly. Annual testing involves a more comprehensive evaluation of the pump's performance, including flow and pressure testing. The results of all testing must be documented and maintained for review. The specific requirements for electrical installations in fire pump systems are detailed in NEC Article 695. This article provides guidance on all aspects of the electrical installation, including wiring methods, overcurrent protection, control circuits, and power sources. It is essential that all electrical work on fire pump systems be performed by qualified electricians who are familiar with the NEC and NFPA 20, the standard for the installation of stationary fire pumps for fire protection. Understanding voltage drop is crucial when designing the electrical system for a fire pump. Voltage drop refers to the decrease in voltage that occurs along a conductor due to its impedance. Excessive voltage drop can cause the fire pump motor to operate inefficiently, overheat, and potentially fail. The NEC recommends limiting voltage drop to 5% from the source of supply to the fire pump motor. To calculate voltage drop, several factors must be considered, including the length of the conductor, the size of the conductor, the current flowing through the conductor, and the conductor's impedance. The NEC provides tables and formulas for calculating voltage drop in Chapter 9. Proper conductor sizing is essential to minimize voltage drop. Larger conductors have lower impedance and therefore result in less voltage drop. When sizing conductors for a fire pump, it is important to consider not only the ampacity requirements of NEC Section 430.22, but also the voltage drop requirements. In some cases, it may be necessary to use conductors larger than those required by ampacity considerations to meet the voltage drop requirements. The utility company should be consulted to determine the available fault current at the service entrance. Fault current is the amount of current that would flow during a short circuit condition. The available fault current is an important factor in selecting overcurrent protective devices, such as circuit breakers and fuses. The overcurrent protective devices must have a sufficient interrupting rating to safely interrupt the available fault current. The interrupting rating is the maximum amount of fault current that the device can safely interrupt without failing. If the available fault current exceeds the interrupting rating of the overcurrent protective device, the device could fail during a fault condition, resulting in a dangerous arc flash and potential equipment damage. The utility company can provide information on the available fault current at the service entrance. This information is typically expressed in terms of symmetrical root mean square amps. The overcurrent protective devices must be selected with an interrupting rating that is equal to or greater than the available fault current. Arc flash hazard analysis is an important consideration when working on or near energized electrical equipment. An arc flash is a dangerous electrical explosion that can occur during a short circuit condition. Arc flashes can generate intense heat, pressure waves, and projectiles, which can cause serious injury or death. An arc flash hazard analysis is a study that identifies potential arc flash hazards and determines the appropriate level of personal protective equipment, or PPE, required to protect workers from these hazards. The results of the arc flash hazard analysis are typically documented in an arc flash hazard report, which includes information on the incident energy levels, working distances, and required PPE. The NEC requires that arc flash hazard labels be placed on electrical equipment to warn workers of potential arc flash hazards. These labels must include information on the hazard risk category, the required PPE, and the arc flash boundary. Workers who are working on or near energized electrical equipment must wear appropriate PPE, including arc-rated clothing, gloves, and face shields. Training is essential for workers who are working on or near energized electrical equipment. Workers must be trained on the hazards of electricity, the proper use of PPE, and the safe work practices. The training must be documented and updated regularly. The NEC requires that all electrical work be performed in a safe and workmanlike manner. Safe work practices include energizing equipment before working on it, using insulated tools, and maintaining a safe working distance from energized parts. The NEC also requires that all electrical work be inspected and approved by a qualified electrical inspector. In addition to the NEC, there are other codes and standards that may apply to fire pump installations, including NFPA 20, the standard for the installation of stationary fire pumps for fire protection, and local building codes. It is important to be familiar with all applicable codes and standards before beginning any electrical work on a fire pump system. When upgrading an existing electrical service to accommodate a new fire pump, it is important to consider the capacity of the existing service equipment. The existing service equipment must be able to handle the additional load of the fire pump without being overloaded. If the existing service equipment is not adequate, it may need to be upgraded. Upgrading the service equipment may involve replacing the service entrance conductors, the service disconnect, and the metering equipment. The size of the new service equipment will depend on the size of the fire pump motor and the other loads on the electrical system. A load calculation must be performed to determine the total load on the electrical system. The load calculation must take into account all of the connected loads, including the fire pump motor, lighting, HVAC equipment, and other appliances. The load calculation must be performed in accordance with the NEC. After the load calculation has been completed, the size of the new service equipment can be determined. The new service equipment must be sized to handle the total load on the electrical system with sufficient capacity for future growth. When selecting new service equipment, it is important to consider the interrupting rating of the equipment. The interrupting rating must be equal to or greater than the available fault current at the service entrance. The new service equipment must also be listed and labeled by a recognized testing laboratory, such as Underwriters Laboratories, or ALL. The installation of the new service equipment must be performed in accordance with the NEC and all applicable local codes and standards. The installation must be performed by a qualified electrician who is familiar with the NEC and the local codes and standards. After the new service equipment has been installed, it must be inspected and approved by a qualified electrical inspector. A fire pump installation requires careful coordination between various trades and professionals. Firstly, the electrical contractor is responsible for the electrical installation, including the wiring, overcurrent protection, control circuits, and power sources. The electrical contractor must be licensed and qualified to perform electrical work in accordance with the NEC and all applicable local codes and standards. Secondly, the fire protection contractor is responsible for the installation of the fire pump, piping, and other fire protection equipment. The fire protection contractor must be licensed and qualified to perform fire protection work in accordance with NFPA 13, the standard for the installation of sprinkler systems, and all applicable local codes and standards. Thirdly, the mechanical contractor may be involved in the installation of the fire pump, particularly if the pump is driven by an engine. The mechanical contractor must be licensed and qualified to perform mechanical work in accordance with all applicable local codes and standards. Fourthly, the building owner is responsible for ensuring that the fire pump installation is properly designed, installed, and maintained. The building owner must also ensure that the fire pump is tested regularly in accordance with NFPA 25. Finally, the local building and fire officials are responsible for inspecting and approving the fire pump installation. The building and fire officials must ensure that the installation complies with all applicable codes and standards. Effective communication and coordination between all of these parties are essential to ensure a successful fire pump installation. Regular meetings and site visits can help to identify and resolve any potential issues early on. Detailed documentation of all aspects of the installation is also important. This documentation should include drawings, specifications, test reports, and inspection reports. It is also helpful to have a designated project manager who is responsible for coordinating the activities of all of the parties involved in the installation. The project manager should be knowledgeable about fire pump installations and should have experience in managing complex projects. Fire pump systems are critical life safety systems that must be properly designed, installed, and maintained. By following the guidelines and recommendations in this discussion, you can help to ensure that your fire pump system is reliable and effective in protecting your building and its occupants.